Okay, so before we dive into related rates here, I want to talk about something that's really important. So I don't want us to get to stumble on this concept. So like let's just say hypothetically, so like if I have a function here, f of x, right? F of x equals to, I don't know, x squared plus 7x, let's say, right? If I get the derivative of this, this is 2x plus 7, right? And when I write this down like that, what's the derivative that I'm getting? I'm getting the derivative with respect to what? X, right? So this is typically implied, right? I'm getting the derivative of f with respect to x. Okay. Now, you guys remember, let's say if y is a function of x, and you have, for example, you're going to get the derivative of, I don't know, x squared plus y squared equals to 4x minus y, let's say. So something like that. So what is that called when we did that?
Implicit.
That's implicit differentiation, right? So here when I do this, I'm getting the derivative of both sides with respect to x, but notice here I have x's and y's, and the key thing here is that y is a function of x, right? So now when I get the derivative of y, what rule do I have to use? I have to use the chain rule, right? Because y is a function of x. So here, what happens is I get, what's the derivative of x squared? 2x. Okay. And then what's the derivative of y squared? 2y times the derivative of y with respect to x, right? That's because y is a function of x, right? You with me so far? Okay. All right. And then this is equal to 4 minus dy over dx again, right? Okay. Now, all right, so those are just kind of reminders here. Now suppose, I don't know, y is a function of, say, t, and I had something like t squared plus y squared equals to 4t minus y. So I'm trying to ease you guys in here. So what's the derivative of that? 2t plus 2y over dt, right? Equals to 4 minus dy over dt. Okay, so what's different about that compared to the line above? Yeah, there's nothing different about them, right? So one is a t, the other one's an x, but it's exactly the same thing, right? You guys with me? Okay, so nothing, weird or scary about t. Okay, so now let's take it one step further. Now suppose that x is a function of t and y is a function of t. Okay? And now I have x squared plus y squared equals to 4x minus y. Okay. Now, let's say I take the derivative not with respect to x, but with respect to t. Now, what's different here is that both x and y are functions of t. So how is that going to change then? What am I going to have? What's the derivative of x squared since it's a function of t? 2x times derivative of x with respect to t, right? Because x is a function of t. Does that make sense? Okay, and then plus 2y times the derivative of y with respect to t, right? Because again, we're getting the derivative with respect to t. Yeah? And then what does that equal to? 4 derivative of x with respect to t minus derivative of y with respect to t. Okay, so the key thing here is, and this is what we're going to be doing with related rates, is that we're going to have things that are dependent on t, which is short for four-letter word, time, right? Exactly. Okay, so, and we may have more than one quantity that is a function of time, and those quantities might be related. Therefore, we call them related rates. But really, this is when we get the derivative of functions, that are functions of t, just because there's more than one of them potentially it's really no different than what we've been doing before. Do you guys agree? So that's all I wanted to make clear, is that this is really not different from the implicit differentiation we've been doing so far. Yes? So far, so good? Okay. All right. So any questions about any of these related rates preliminaries? No. Okay. Let's get with it then. I've got some problems here prepared for us. All right, so let me kind of do a little bit of setup for you. So we have a balloon here, and we're saying that the volume is increasing at a rate of 3 cubic feet per minute. Okay, so you don't have to draw this, but I just want to draw it for you. I'll erase it in a minute here. So you got this balloon, right? And you put in 3 cubic feet per minute, right? So if you just kind of imagine here, this balloon, so imagine it's flat, right? And you put in 3 cubic feet of air, right? So then what happens? Well, after a minute, it'll be bigger, right? Okay, now, okay. Now here, this has a certain radius, right? And it has a certain volume. The volume at this point is 3. If I wanted to find the radius, would I be able to? If I know the volume is 3? Yes, good, okay, all right. I won't, just because it's not really necessary here at this point, but we could if we wanted to. Okay, now, what I want to get at here is, so here we're looking at 1 minute, after 1 minute, and then after 2 minutes. So after 1 minute, the volume is 3, right? Because you're blowing air 3 cubic feet per minute, right? After another minute, it's 6. After another minute, it's 9, and so on and so forth, right? Okay, now, so the volume is changing 3 feet per minute, right? Now, notice at the same time the volume is changing, the radius is also changing, right? Now, what's it changing by? Well, we could find it if we really felt like it, right? The volume, what's the volume of a sphere? 4/3 pi r cubed, right? This is volume. Okay, now if you really wanted to, you could plug in 3 right here, right? Solve for r and whatnot, and you would get r is equal to whatever, right? So it's not really relevant. But the point is that as one quantity changes, in this case the volume, the radius is also changing, and the two rates depend on each other, right? So like if you blow air faster, the volume, if you blow more air, so instead of 3 cubic feet per minute, maybe you do 10 cubic feet per minute, will the radius change at a different rate, or will it always stay the same? It'll also grow faster, right? So the two rates are related. That is right. Okay, so that's kind of what we're talking about. Okay, so that's sort of the idea, just kind of the big picture idea of what's going on, is we have different rates that are related, and we want to figure out something about one or the other, right? So in this case, notice that the rate at which we blow the air in is constant. Okay, so that's fine. So it's this 3 cubic feet per minute. And then the question is, how fast is the diameter of the balloon increasing when the radius is 1 foot? Okay, now, so what I want to do here is I want to give you a strategy that you can use for these. And we'll kind of go through and do it here. Okay, now, so hopefully we have enough space to do it here. All right, step 1. Draw a picture and label. Now, a couple of important points. Rates are derivatives, right? Because that's what a derivative is. It's a rate of change. And I think I'll just make a note here. Be careful with constants. And I'll point it out as we go forward, where we have to be careful with there. But okay, so let's do that. So if I take a look over here and I'm going to draw, well, what's my picture? Well, it's a sphere, right? So I'll draw that. And then I'll just label as much as I can here that's relevant to the problem. So notice I'm given volume, right? So, and I'm given this quantity, 3 cubic feet per minute. What is that 3 cubic feet per minute? It's a rate, right? It tells me how fast something is changing. And what did we just say? Rates are derivatives, right? So what you want to do is take a look at the units, because that's going to tell you what kind of derivative it is. Sometimes it's obvious, but other times you want to be a little bit more careful and just look at the units, because that'll tell you. So, so what is it the derivative of? It's the derivative of the volume, because it's telling me how fast the volume is changing, right? With respect to time. And notice, what are the units? On top, what do I have? Cubic feet, which is a measure of volume, right? And minutes, which is a measure of time. So it's all really all in the units. So what is that? That's equal to 3. Done. Okay, good. Good job. Now, over here, I have a question. How fast is the diameter of the balloon increasing when the radius is 1 feet? Okay, so I'm going to put this as actually a part of the first step. Write down the question in math notation. This is very important. If you don't do this step, the writing down the question, you can end up spinning your wheels trying to figure out, just calculating all kinds of stuff, going this way and that way and who knows where. And you'll never really get to where you're trying to go. So writing down the question solidifies what you're looking for, and that'll allow you to make good decisions going forward. So what is my question? The question is asking me for how fast something is changing. That means I'm looking for a rate, also known as a derivative. Okay, good. All right, so let's see here. Okay. Question. What is the derivative of the diameter with respect to what? Time. Exactly. Because it's how fast is something changing. So with related rates, it's always going to be with respect to time, with respect to t, because we're talking about how fast things are changing. And so it's pretty much 99% of the time with respect to time. So, okay, now this is equal to question mark, because that's what we're looking for. And you almost always have this, the when. Now, so here notice it says when. This tells us specifically what point in time we're looking at to answer this question. So we're looking for the rate at which the diameter is changing, not all the time, because it's not necessarily constant. We're looking for it when? When the radius is 1 foot. When r equals 1 foot. Okay, so that when part is critical, super important. Now, does this tell me that the radius is always equal to 1 foot? No, it's just telling me a specific point in time, which is when I'm looking for to answer my question. Okay. All right, strong work, team. Good job. Step 2. Well, first, any questions with step 1? Okay. Step 2. Write down a formula that relates your info. Now, very important, info involves the question because we need to make sure we're answering the question. So we want to look at, what we're given, what we're looking for. Make sure that whatever formula you write down, it's related to what you have and what you're looking for. So here it's pretty obvious what the formula is. We have a sphere. What formulas are related to spheres? Well, we have the volume of a sphere. We have the surface area of a sphere. We have, well, it's a sphere, so it doesn't really have a circumference. But so which one seems more reasonable? We really only have 2 choices. The volume, right? Why the volume? Because we're given the volume, right? The rate at which the volume changes. We're not given any information about surface area, so that doesn't really make sense to use a surface area. So that's the thinking. So what's the volume of a sphere? We just said earlier. 4/3 pi r cubed. Okay. Step 3. Take the derivative of both sides with respect to time. Take the derivative of both sides and plug in your info star. More work may be necessary. Okay, so we plug in everything. Well, no, sorry, we get the derivative of both sides. So let's see here. So the derivative of the left side and the derivative of the right side. Okay, so here we'll use what we talked about a little while ago. What's the derivative of the left side? No, left side. Left side. What's the derivative with respect to t of v? What is v? V is the volume, right? And what is volume? Is volume some variable, random, or is it a constant? No, it is a function. A function of what? Well, it is a function of the radius, yes, but it's mainly what's the relevant part here in this scenario of time, right? Because we're getting the derivative with respect to time, and the volume is a function of time, right? As time passes, what happens to the volume? It changes, right? It increases. So, okay, so what's the derivative of the left side then? dv over dt, exactly. So if we would be using the chain rule, if we were doing this explicitly, we would say, oh, well, it's 1, right? Because it's just 1v. The derivative of v is 1, but then times the derivative of v with respect to t, right? So we typically don't put the 1 there, so we just leave it like that. Okay, now what is that equal to? What is r? R is the radius, which is a function of time. Exactly. As time is changing, r is also changing, right? So r is also a function of time. So here you should put a star here. V and r are both functions of t. So v of t and r of t. Now, do you know explicitly what they are? Well, not necessarily. Well, v you actually do know. But r, you don't really know what it is as a function of time, right? Does that mean that you can't get its derivative? No, right? We've been getting derivatives even if we don't know what the function is, right? Isn't that what we did right here? When we have y as a function of x, you don't really know what it is, but you can still get the derivative of it, right? It's the same thing, it's just the variables are different. You know, instead of y and x, you have r and t. That's it. It's the only difference. It's identical otherwise. Okay, so now what's the derivative of the right side? Do I do the product rule? That's exactly right. 4/3 is a constant. Pi is a constant. So what do I do with 4/3 pi? I just leave it alone, right? 4/3 pi, leave it alone. Okay, what's the derivative of r cubed? Times? dr over dt, right? And then 3's cancel, right? Okay, so any questions right now? Is that okay? That's not that bad, right? Okay. All right. So, what else do I do? And then we plug in our info. So what can we plug in? We know dv over dt is 3, so we can plug that in. What else?
The radius 1.
dr over dt. Do we know what that is? Nope. R is 1, right? R is 1.
We're looking for that.
Okay, now I have a question. Actually, before we do that, why did I not plug in 1 right there? What is it? A lot of you guys responded, but I couldn't catch any one. Because r is a function, right? The r equals 1 represents a point in time. So you can't just plug it in, because if you plug it in, you would be saying that r is always equal to 1. Does that make sense? So if you're given a number, make sure that it's clear whether it's a constant or if it just represents a value at a specific point in time. So that's why we do not plug it in right there. Okay. Now here we have a bit of a problem because what's my problem? I have dr over dt. What am I actually looking for? The rate at which the diameter is changing. So so this is a bit of a sad situation here. What can we do? Well, we can fix it. But it's a good lesson, because see, if we wouldn't have made this mistake, then you would have never had to look for it. Okay, notice right here we have the formula, V equals 4/3 pi r cubed, right? Our question is asking us for the rate at which the diameter is changing, right? So before I get the derivative here, you need to make sure that what you're looking for is in there, so that when you get the derivative of it, you end up with what you're looking for, right? Does that make sense? So I need to fix this so that I don't have r in the formula. I need to have d in the formula. So that's an easy fix, though, actually. What is r? R is just d over 2. So that's all right. We can fix that. No big whoop. So, okay, but then now we have to go back a little bit here. Okay. All right. So I still have the 4/3 pi here, but then what's the derivative of d over 2 cubed? So I still have 3, right? Times what? What's the derivative of d over 2 quantity cubed? 3 times what? D over 2 squared. Yep. Times the derivative of d over 2, which is 1/2. Good. Derivative of d with respect to t. Yep. Now it would have been much easier to have done what? Just cube d over 2 first, right? And then... But that's okay. I wanted to do it anyways. So now let's see here. So we can still plug in 3 right here, right? No big deal. This 3 still cancels with that 3. Now, what about D this time? What is D? If R equals 1, then D equals 2, right? Right? Okay. So then what? So 3 is equal to, let's see, 4 pi. I've got 2 over 2, which is 1. 1 squared is, that's the number 1, right? Times 1/2 dd over dt. So this implies that dd over dt equals 2. 3 over what? 3 over 2 pi, right? Because the 4 and this 4 and this 2 reduce to 2 and 1. So what is that about? That's about, if pi is about 3, that's about 1/2, right? So the diameter is changing at about 1/2 feet per minute, right? Does that make sense? Does that mean it's always changing at a rate of 1/2 foot per minute, roughly? No, only when the radius is 1, right? Does that make sense? Cubic feet? No, just feet, because it's diameter.
What do you mean by half?
Oh, just 3 over 2 pi. Well, because pi is about 3-ish, right? So it's about 1/2. I mean, just to approximate it, you know. You don't need to. You could have left it like that. Okay, now, questions. Feet per minute. No? You guys are good? Okay, now, so this strategy, keep it, staple it on your forehead. No, maybe not on your forehead, because then you can't see it. Staple it on your arm, your forearm. Okay. Are you guys ready to do another one? Okay, the world famous ladder problem. It's one of the classics. Classic related rate problem. So here we have a 13-foot ladder is leaning against the wall. So let's draw. So if I draw a wall here, wall there, let's say my ladder, let's say my ladder is orange. Okay, so my ladder is 13 feet, right? Now notice, is this ever going to change? No, right? Because the ladder is 13 feet long. The length of the ladder does not change because, well, I guess it's an old school ladder. You can't extend it, apparently. Okay, so it says if the bottom of the ladder is pulled along the ground away from the wall at a constant rate of 5 feet per second. Okay, so what is that? What does that describe? The rate, yep. So it's going to be a derivative, right? Okay, so it's telling me that the bottom of the ladder, which is right here, is being pulled away from the wall 5 feet per second at a constant rate. So you're taking basically the bottom of the ladder and you're pulling it away from the wall 5 feet per second. Okay, so we should label this distance here. What do you guys want to call that? The distance from the bottom to the wall. What do you want to call it? You can just pick a letter, any letter you want. N? L. Well, yeah, well, X, L, X. Let's do X. Okay. X's are pretty popular. Any letter, really, is fine, but X is good. Okay, so now notice, why do I label it X and not a constant number, like the 13? Yeah, it's changing over time, right? Okay, so that's the difference. Okay. Now, let's see. Now we have our question. How fast will the top of the ladder be moving down the wall when it's 8 feet above the ground? So, how fast will the top of the ladder be moving down when it is 8 feet above the ground? Okay, so I should label this something. What should I label that? Really? H? But I labeled this one X, so yeah, it should be Y, right? Okay. X and Y, L and H, it doesn't matter. You can pick whatever you want. A's and B's, Z's and Q's, epsilons and deltas. But X and Y is pretty common. Okay. All right. So, do you guys think that Y is going to change 5 feet per second as well, just like X is? Well, then we're done. There's nothing to do because that's the question. 5. So, done. Okay. Probably not, because then we wouldn't be here. Okay, so
What's 8 feet says? 8 feet above the ground.
what's 8 feet above the ground? Okay, so how should we deal with this? Well, okay, what do you guys think about putting an 8 right here? How do you guys feel about that? No, you should feel terrible about doing this. Okay, so this is one of the biggest mistakes, one of the biggest problems, is make sure you're careful with the constants you're given. Make sure that if you put a number down on your picture, it has to be a constant. If you put a number and it represents a specific point in time, you don't want to put it on the picture. You're going to use it at some point, but you don't want to put it on the picture because it'll mess up absolutely everything. So, so notice it is incorrect to put this 8 here. This is Y. Why is it Y? Because it's changing, right? As the bottom of the ladder goes away, the top goes down, so that's a variable quantity, right? Okay, all right, so that's super important. Okay, now, what part are we missing here? We're still on step 1. We haven't finished step 1 of our strategy. What part are we missing? Write down the question. Yes, this is key. Okay, so very important. Write down the question. What is the question? How fast is what? Okay, so what letter is that? dy over dt, right? How fast is this quantity changing? This one right here. How fast is y changing? Okay, and then what? What am I missing? When. Okay, so this is key. When y equals 8, right? That's where I'm going to use it. Only at that point. Only when I'm at the end. Once I've gotten the derivative of both sides, then it's okay to plug in the 8 for the y. Does that make sense? Okay, so questions so far? Don't know where to start. Okay. All right. So it's really important that you get this down from the beginning. You know, so you want to make sure that you don't just kind of slapdash put down the stuff wherever you feel like it. You want to have a system, right? So the system is you draw your picture, you label everything, and then you write down your question. And you need to make sure that you have the question clear and what point in time you're talking about. And if you put a number down, it has to be a constant, right? Notice we have two numbers right here, 5 and 13, right? Both of those are constants, right? Now we actually have not fully labeled this one. What is this? This 5. It's a rate, right? So it's the derivative of x with respect to t. It's the rate at which x is changing. Yeah? Okay. So actually I'm going to write it down up here because I don't want to run out of room. Okay. So I'm going to erase it here and then I'm just going to put it right here. Okay. All right. So that was step 1. Step 2. What is step 2? Formula relates our info, right? So we have x, we have y, we have the 13. So it's a triangle, right? So what are the possible formulas? We have the area of a triangle, we have the perimeter of a triangle, we have the Pythagorean theorem, we have all the trig functions, right? Because it's a right triangle, so there's an angle right here somewhere, and you've got... Okay, so there's a lot of formulas going on. But there's only one that you care about, and it's the one that's related to the information you're given, that you have in your question. So what's the natural choice? Good, okay. I'm glad you guys did not say area, because that would have made me very sad. Okay, so... Pythagorean theorem, what is it? X squared plus y squared equals to 13 squared, right? So far so good? Alright, so then what do we do next? Derivative of both sides. You could solve for y if you wanted to. But typically it's easier to just get the derivative implicitly. Because if you solve for y, then you have radicals. But that would work too, if you can. Okay, so then what's the derivative of the left side? 2x dx over dt. Yep. Plus 2y dy over dt. Yep. 0. Yep. Okay, and then after you do that, then what can we do? So we plug in what we have, right? So let's see here. So what comes to mind that we can plug in?
dx dt.
Okay, so dx over dt is 5, so that's good. Dy over dt is the question. That's right here, so that's okay. We're just going to leave it there. What about x and y? Do we know what x and y is? We have y, yep. Y is 8. Notice how it's okay to put 8 in for y now, just not before you get the derivative of both sides, right? Okay, now we're missing x, right? So this is the more work that we often have to do is, well, I don't have x, right? But can we find x with the information we have?
Yes.
Yeah. So this is a little bit more work. More work. Find x when y is 8. So that shouldn't be too difficult, right? Because I have a triangle, right triangle. If I know this is 8, this is 13, what is x equal to? It's the square root of 13 squared minus 8 squared, right? And what is that? 105, yep. Square root of 105. 10-ish, yep. Okay, so then if I have that, another thing that you notice you can simplify is if I divide through everything by 2, 0 divided by 2 is 0, right? So just a little simplification there. All right, so then what is dy over dt? It's equal to 5 root 105, right? Divided by 8, right? If I solve for dy over dt. And so that's about, what is that about? That's about 11 over, so 60 over 8-ish. Yes. It should be negative. Thank you. Does it make sense that it would be negative? What does it mean when a derivative is negative? It's decreasing, right? Does that make sense in the context of the problem? Sure, right? Because it's going down, so the value of y, which is the height, basically, the value of y, notice it's decreasing. So it makes sense that its derivative would be negative. Yeah? Okay, questions? No? You guys are okay? All things considered? But notice, is the approach much different from the first one? Not really, right? The formula is different. A little bit of the specifics are a little bit different, how you plug in things. But really, the strategy that we applied was really the same, right? Did the second one feel easier than the first? That's because you've done the one before. So see, now when we do the next one, it's going to be even easier, yeah. But then when you get home, it gets harder again, because I'm not doing it. You guys are going to do it. So. But that's all right. Then it gets easier again. Okay. All right, so I would let you guys do one, but honestly, you'll just spin your wheels at this point. So I think it would be better if you guys have like a good solid chunk of examples, and then you can kind of work through them again back at home, and then use the other ones that you have, the other videos too, so you have a lot of examples as a solid foundation, you know. Unless you guys really want to try one on your own. No, okay. That's what I thought. Okay. All right. So, next one. Baseball. Who doesn't like baseball? I don't like baseball, actually. But softball, okay. Even worse. No, I'm just kidding. Sorry. Just kidding. It was a joke. Told you, math jokes are terrible. All right. So, we have a softball diamond. It's a square whose sides are 60 feet long. Suppose that a player running from first to second base has a speed of 25 feet per second at the instant when she is 10 feet from second base. At what rate is the distance from home plate changing at that instant? What do you guys think? Draw a picture. That's right. All right. I thought you guys were going to say 25. But okay, so draw a picture. Got a baseball diamond. Here's home plate, right? So for those of you that have never played or seen in your life, softball field. Home. Okay, so there's home, first base, second base, third base. Okay, so let's see. So the player is running from first to second base. Okay, so the player is somewhere over here. Ta-da! And the player's running this way, right? And the player's running 25 feet per second. And what else? What else should I put down on my picture? 60 feet. Oh, yeah, so this is 60, right? So it's a square, so they're all 60 feet. What else?
10 feet from second base.
Okay. 10 feet. What else? Yeah, Calvin.
How were we supposed to put that on there? It's not constant.
Excellent detective work there. Good job. You are correct. We do not put this on here. All right, do you guys catch that? Why is it not okay to put the 10 there? Because 10 is just a specific point in time, right? So what should we? So what you should do is those numbers that you get that represent a specific point in time, you should, grab a hold of them, note them, and put them in the question, because that's where they go. That's when you're going to plug it in, when you're ready to answer the actual question that you're being asked. So, don't forget about it. So it's right here, right? 10 feet. And then actually there's another one. Is this 25 constant?
Yeah.
Nope. See, it's telling you at the instant. Right? So this is also not technically okay, although that probably wouldn't have messed us up probably as bad. But this one would. So you got to be careful with that one. So, but anyways, so I can integrate this into my question. What's the question asking me for? The derivative of what? Distance from home plate. Okay, well, what is that? Well, we got to draw it, right? So the distance from my player to home plate, let's call it big D. Okay. So what's the derivative of big D with respect to t, right? And let's see. When? Well, let me leave it at purple. Okay. When something equals 10. What is the something?
D.
Nope. What's my problem? I'm missing variables. I'm missing letters representing quantities. That's why you're drawing a blank, because there's no letter. Yeah, I need to draw a line, right, that represents that quantity and put a letter, give it a letter, right? Because that's going to represent that quantity, but it's a variable, right? It's changing. Meaning, so what I want to do is, so I'll draw a line from here to here, right? So this line right here, this distance, let's see. So give me a letter. Y. But why? Okay. Y. So this is when Y, which is changing, right? This quantity is changing. The distance of the player to second base. But now I can say, okay, well, at the moment when Y equals 10, right? So if you're ever missing a variable, well, then just stick it in there, right? And you can pick whatever letter you want. It's no big deal. Okay, when Y equals 10, and what else? What about this 25 business? What is that? The rate of what? Or with respect to t, right? But what's that? What rate does that describe? Okay. So what quantity is that related to? It is feet per second, but what variable? Is it big D or is it Y? Or another variable?
I think that would be D. Big D?
No, it's Y. Right? Isn't that, so that Y, that distance Y that you see, as the player runs, Y is changing directly, right? So the derivative of Y with respect to t is 25, but it's actually minus, right? Because Y is decreasing, right? Does that make sense? Okay. So, because Y is decreasing.
Or does it say that she running juice?
Well, because if you're running from first to second base, then Y has to be decreasing, right?
But it's always at a constant speed of 25 feet per second, right?
No, it's at that instant it's 25 feet per second. You guys don't seem to like the negative. So, well, okay. So let me see here.
Is that because it's getting closer to home base? Or?
Because you're getting closer to second base. Yeah. So here's the runner, right? And then if I have this distance right here is y, right? If I say dy over dt is equal to 25, what is this telling me? This is telling me that y is increasing, right? Over time. Now, if the runner's going this way, is y increasing? No, y is decreasing, right? At that same rate, 25, right? It's getting smaller. So it's not increasing, it's decreasing. Now, you have actually another option here. Since you mention it, since you're uncomfortable with this negative business, which is okay. I mean, you can get used to it over time. Let's say I draw a different picture. So now let's say, so here's my runner, right? Here's second base. Here's home. And here's first base. So here's big D. Now, let's say you label it a little bit differently. Let's say you label this quantity y instead. You with me? Okay. So if I label this quantity y, then what would this, or better yet, what would be the question in this case? The derivative of d with respect to t is equal to question mark when y equals to what? 50, right? So instead of phrasing it this way, when y equals 10, using directly what we're given, it's a little bit awkward, right? Because we haven't really gotten to it, but what's the formula we're going to use? Well, look at the triangle there. It's a little weird looking, isn't it? Is it a right triangle? If you draw, what would you do? You would draw, I guess, a line from second to home base, maybe? I don't know what you guys were planning, but I'm just saying that if you look at it this way, this is a right triangle right here, right? And you can rewrite this as when y equals 50, right? Because that's what this is, right? And in this case, what would dy over dt be? Positive 25. Why? Because now y is something different. Y represents this distance, right? And now as the runner goes towards second base, now y is increasing. Does that make sense? Do you guys see the difference between the two? So either one is fine. And it's also okay to, start drawing it one way and then decide, oh, well, I think it makes a little bit more sense to think of it this other way. But either way would work. The problem with this one is that you've got this quantity and this quantity right here. And then what would be your formula that relates your info there? Well, it would be the Pythagorean theorem, right? But the problem is that what's this side right here? I'm kind of cluttering my picture here, but I think I'm just going to erase it and redraw it. But that's going to be 60 minus y, right? And so now my formula is going to have a 60 minus y squared, which is more messy than just having a y squared, right? So there's pros and cons. So, at the end of the day, either one would work. But if there's more than one option, typically one of the options is a little bit easier than the other. Okay. So, do you guys want to do the green triangle up high or the orange triangle on the bottom? Orange, okay.
If we use the first picture,
Yes.
you can say that gonna be
Well, it is if you look at this one down here. But no, this one over here would not be. Is that what you're thinking? Yeah.
Yeah.
Okay. You can, yes. And it might work, but it probably will not. So, because you don't have any information about angles. Okay, so now let's just kind of redraw here. So I've got this right here, this. So this is a constant 60. This is big D. We're going to label this Y, and we said we're going to change this to when Y equals to 50. And then, well, I'm not going to put that there. Okay. And when dy over dt is positive 25. Okay, so there it is. That's our modified problem. All right, so what formula are we going to use? Pythagorean theorem, the same one that we did last time, right? So y squared plus 60 squared equals to d squared, right? And then if I get the derivative of both sides, what would I get? 2y dy over dt plus 0, right? Okay, equals to 2d dd over dt. Okay, so then let's take a look. Let's see what do we have? What do we need? So we have y, right? Y is 50. We have dy over dt. That's 25. Do we know what d is? We can find it, right? So this is more work. We need to find. So find big D. So what would D equal to? The square root of 50 squared plus 60 squared, right? So what is that? 2500 plus 3600, which is? How many? 2500 plus 3600? 60. 6100. Yep. Let's see here. So square root of 6100. Let's see. And then we can get rid of the 2's, right? Let's see. So then dd over dt is equal to 50 times 25 divided by 6100. That's the same as 10 root 61, no? You guys agree with that? So then, I don't know, 125 over 2 root 61. Does that sound right? So what is that about? So if we just kind of approximate, square root of 61 is pretty close to 8, right? So times 2 is 16, so 125 over 15, 14-ish. It's about 8-ish. Does that sound about right? 8. No, that doesn't sound right.
That's 2 root 61.
Would the 2 go away?
Shouldn't it be over root 61?
Doesn't 2 go away?
You cancel out the zeros from 50 and 10.
Oh, yeah. Yeah, that's what it is. Okay. Yeah, I don't know why I put the 2 there. Yeah, I don't know what I was thinking. Yeah. So now that makes sense, right? So 125 over square root of 61. about 1.6. Yeah, what is it? 125 divided by square root of 61? 16. Any questions with that? No? You guys are okay? I had one more, but I think it's about a rocket ship. Do you guys want to do it real quick, or?
Yeah.
Really? Yeah. Okay. All right. Rocket ship. We'll do it quick because we don't have much time. Okay. So we've got a rocket ship. See? It looks kind of more like a lamp, but it's a rocket ship. I don't know what that is. It's a candle. It's a rocket ship in the shape of a candle. I don't know. Never said I could draw. Okay, so it's going up. It's going up that way. Oh. Okay, so let's see. It's tracked by a radar station that's on the ground 5 miles from the launch pad. So here you got some radar station. Radar station. Rocket. Okay, so 5 miles, right? And then the question is, how fast is the rocket rising when it is 4 miles high and its distance from the radar station is increasing at a rate of 2,000 miles per hour? Okay, so I think there's a few pieces of information here. So I think I'll draw a line right there and draw a line right there. Okay, so notice this right here is it's changing, right? So I'm going to label that Y. Is this changing? Yes, I'm going to label it D. Is this changing? No, I'm going to label it 5. Okay, I had already labeled it 5, but I'm going to put it closer. Okay, now let's see. So that sounds good. All right, so then what's the question? How fast is the rocket rising, right? When what?
2,000 miles.
When what is 2,000? d over dt is 2,000, right? The rate, the the distance from the radar station, right? Okay, and what else?
And 4 miles.
Y is 4, right? Okay, but notice that we did not put 4 on the picture or 2,000 on the picture because they represent points in time, right? Okay. So this is pretty similar to the other one, right? So what would be our formula? Y squared plus 5 squared equals to D squared. And then? Derivative of both sides. Now notice, is this easier than the one that we just did? It is now, right? Because we already did one. So see, it's getting easier. It's getting easier for me to do them. I'm just kidding.
It's easy because we same as before we using Pythagorean, but what if we have something
Like an angle.
yeah, or something more difficult?
Well, yeah, then you'll do that one, and then you'll do several like that, and then it'll be easy again, you know? It's only hard the first time. Or second time, or first through the 5th, maybe. All right, but by now, we're experts at this Pythagorean theorem business, right? Look at this. We can do this in our sleep. 2d dd over dt. Plug in all of our stuff. See? We didn't even need to stay an extra 5 minutes. We could have done this in our sleep. What's this? This is the question, right? D is 2,000. Oh, this is even easier than the other one we were given. Oh, wait, no. Sorry. Misread. Okay, 2,000. And then we need to find D. What is D? Square root of. Well, I probably shouldn't put it on the picture, actually. Square root of 5 squared plus 4 squared. Okay. So dy over dt is equal to, so the 2's cancel, right? What is that? 25 plus 16? Over 4? Whatever that is. Yes? No? No? What did it? Oh, yeah, sorry. I was in the last problem. 6? 25 plus 16? No. 25 plus 16? 25 plus 16 is, yeah, 41. Yeah. Oh, they were saying 6. It's like, it's not 6.
What was that you were saying about the easy stuff from Harvard?
Yeah, this is true. Yeah. Okay. All right. Okay, we're all done. It took us what, 5 minutes? Look at that. That was easy. 5 minutes.